Now if I apply +1 shift to the original signal or give one time delay in the time domain, then in frequency domain it will complete one complete cycle of the circle. For example, if there's one time delay in the original signal, and what will happen in the frequency domain? Here I have 0 0.7 minus j 0.7 minus j minus 1 minus 0.7 and then it will complete one cycle of circle like this. At x of 1 I have x of 0 I have 1, x of 1, x of 2, x of 3, x of 4, x of 5, x of 6 and x of 7. This shows that it completes the one cycle of this circle. Likewise, if I give +2 shift or 2 time delay in the time domain, then in frequency domain 2 complete cycle of circle is completed. Now moving towards the second topic of today's lecture, which is sampling theorem. Sampling theorem states that the minimum sampling frequency, let's say omega s, which is minimum sampling frequency, must be at least twice than that of highest frequency component present in the original signal. It must be 2 times that of maximum frequency. So here I assume x of t analog waveform. The sampling of this waveform can be expressed as the product of this with periodic impulse train p of t. In frequency domain there is convolution instead of multiplication. In the frequency domain it is represented in this form, and this is the sampling of x of t and is expressed as x s of omega. So this is the frequency domain representation or frequency convolution property of Fourier transform. Frequency the periodic impulse train is expressed as, and here ck is coefficient and is found by this formula, and by solving this we get c of k is equal to 1 over ts, where ts is this sampling period. By putting this ck in this formula, we get p of t equal to summation minus infinity to infinity 1 over ts e into j 2 pi kt divided by t. In the frequency domain it is written as p of omega equal to 1 over ts 2 pi impulse omega minus k2 pi divided by ts. Now by putting the value of p omega in the frequency convolution property, we get this and by applying the shifting property, which is x of t convolution t minus t naught, we get x of t naught. This t is replaced by t naught omega t minus t naught. So by applying the shifting property, we get the final result in this form, and this is the proof of sampling theorem. The spectrum of the original signal. This is the spectrum of the original signal, and if I multiply this signal, this spectrum, with impulse train, then we get the spectrum that repeats itself periodically in frequency after every omega s hertz. The spectrum will look like this is omega s. Periodically repeat itself. Now I will explain aliasing. If omega s is less than maximum frequency, then aliasing will occur and spectrum will overlap each other and some of the information will be lost. If this spectrum overlaps, then aliasing will occur. To avoid aliasing, sampling frequency must be greater than the maximum frequency. So there are two ways to avoid aliasing: by increasing the sampling frequency and by applying the low pass filter. First one is by increasing sampling frequency, and second one by applying low pass filter or anti-aliasing filter. The analog signal is pre-filtered so that the maximum frequency is reduced to f over s or omega s over 2 or less, so that there is no aliased component. That is it for today. Thanks.